So let's look at some practical uses for these radical reactions. Radical reactions occur in our atmosphere. Ozone, which is O3, will absorb UV radiation and make O2 and a free radical. Then the oxygen will react with the free radical and remake the ozone, releasing some heat. This is the reaction that shields us from UV. The ozone, the net reaction here is that the UV energy is transmitted into heat, and so is dissipated and doesn't cause us to have sunburns or bad reactions. So the ozone is now missing in parts of Antarctica, and it's thinner everywhere, and it's because we've been using these freons. Freons are composed of carbon, chlorine, and fluorine. They're used as refrigerants, propellants, foam insulation, and for firefighting. And they destroy the ozone. One molecule of radical chloride can destroy many, many molecules of ozone. So the initiation step is a homolytic cleavage, and we get chlorine, fluoride, and chloride, and it's a free radical, and we also produce the chloride free radical. The chloride free radical comes down here in the propagation step and reacts with the ozone and pulls off one of the oxygens and leaves us with O2. Then this is a radical. Then this molecule comes down here and reacts with another oxygen atom and makes O2 and regenerates the chlorine radical. So a chlorine radical can go through this cycle many, many times and destroy many, many molecules of ozone, which is why these freon substances have been banned. Okay. Also, if we look at organic compounds, they will slowly oxidize in the presence of oxygen. The initiation step is a hydrogen extraction, leaving a free radical. This is not a homolytic bond cleavage as most of the other initiation steps that we've looked at are, but instead a hydrogen extraction. The propagation step, our radical is going to react with oxygen, and that will end one end, and then the other end reacts with another organic molecule, extracting the hydrogen, and we get a peroxide. So the sum of the propagation steps must be the net reaction. And so our net reaction is that we take our organic molecule. Let me get my pen to work. Get my magic pen. We get an organic compound plus oxygen, and we make a peroxide. Because of this autooxidation reaction, we have to be very careful about storing ether because we can form a hydroperoxide, and it's explosive. This process, in general, the whole oxidation of organic compounds is dependent on light, and so we store organic chemicals and vitamins in brown glass so that they won't oxidize. Another place we see oxidation is in vegetable oil. Vegetable oils are, of course, long-chain triglycerides, and they're susceptible to autooxidation at the allylic position. So this is our double bond, so that here and possibly here, it would be subject to autooxidation. This will give a rancid smell and spoils the food, so you can't eat it. And we fight this with BHT, which is this molecule right here. I have to changes so that it stay, BHT. And this molecule, if it encounters a radical, is able to, the radical will extract a hydrogen, this hydrogen right here, but this is a resonance stabilized structure, and so it doesn't go on to interact anymore. So that's why we add BHT to many foods. I'm not going to say too much about the acetaminophen, but it's also a radical reaction. Glutathione is a radical scavenger in the liver, and what happens here is that when Tylenol is metabolized, it consumes all of the glutathione, and if all of the glutathione is gone, then the free radicals are uncontrolled, and you end up with liver damage. Naturally occurring antioxidants are vitamins E and C. And next we'll talk about the radical addition.